In this series of videos, we're going to be combining our knowledge of structural chemistry and Lewis structures with our understanding of the quantum model of electron organization. And the first area where we're going to combine these two is with atomic Lewis structures. So if we take a look at carbon, we see that its Lewis structure clearly has 4 unpaired electrons. We know this because this is how carbon makes 4 bonds. But if we compare it to carbon's valence shell in the orbital energy diagram, we see that only these 2 electrons in the 2p subshell are unpaired, and we have a lone pair here in the 2s subshell. So where do these 4 unpaired electrons come from? Well, if we make one modification to its orbital energy diagram, if we take this electron from the 2s subshell and we move it over here to the empty orbital in the 2p subshell, well, now we have carbon with 4 unpaired electrons, and that is that. The problem is that according to the Aufbau principle that states that you can't add electrons to an orbital unless every other orbital at a lower energy level is full, we cannot actually do this. So how can we get carbon to form 4 unpaired electrons? Well, the simple answer is if we were to combine the 2s and 2p subshells into a single subshell, dare I say a hybrid subshell, this would resolve the problem. So if we redraw carbon's orbital energy diagram, so again, the 1s subshell is not affected because these are the core electrons, but if we redraw each of these subshells as a single unit like this, that would mean that all of these orbitals are now at the same energy level. And this hybrid, this amalgamation of the 2 subshells, is what we call the 2sp3 hybrid subshell. Why sp3? Well, because we're combining the 2s subshell, so 1s orbital, with 3 2p orbitals, that means that we can call this sp3, representing all of the orbitals that we have amalgamated together. And because these orbitals are now at the same energy level, we aren't breaking any rules when we fill each of them with an unpaired electron like this. To get this into writing, when carbon forms bonds, when it is able to pair electrons off with each other, carbon's 2s and 2p subshells overlap and combine together to form what we call hybrid orbitals, which are a combination of the s orbital and the p orbitals in carbon's valence shell, allowing it to then pair electrons with other elements in order to make bonds. And we can take a look at how carbon does that by looking at the simplest carbon-hydrogen compound, CH3, methane. So the idea is each of these orbitals that have been drawn here, each of these represents a 2sp3 orbital, and we can see that each of the electrons within there is an unpaired electron. Now, remember that all electrons want to form pairs in order to stabilize, and if we consider hydrogen, remember that hydrogen only has 1 electron in its 1s subshell, which means that this electron from hydrogen can form a pair with the unpaired electron in each of carbon's sp3 orbitals, and when they form pairs like this, that gives us a bond. Now, one of the terminologies that we're going to go over is that there are actually different types of bonds depending on how this pairing occurs. So unpaired electrons from one element and from another element, sp3 orbitals, can overlap in order to form a pair, and this overlapping is what we call a sigma bond, which we represent with the Greek letter lowercase sigma. So again, because this pair is formed by an electron pairing between an sp3 orbital from carbon and the unpaired electron in carbon's 1s orbital here, this overlapping causes a sigma bond. So this means that in CH4, sorry about that mistake, in CH4, each of these overlappings of an sp3 orbital and the s orbital from hydrogen produces a sigma bond for a total of 4 sigma bonds, but as we'll see, this is not always the case. If we take a look at how nitrogen hybridizes in a similar way. So we can recognize that nitrogen has 3 unpaired electrons, which again matches its Lewis structure like this. However, bonding does not occur with non-hybridized orbitals. So if we want to draw nitrogen's hybrid orbitals, again, we're taking the 2s and 2p subshells and amalgamating them together so that we get 4 orbitals on the same energy level. So here's the unaffected 1s subshell. These are the core electrons. And if we redraw nitrogen's 2sp3 hybrid orbitals here, now if we are to add these electrons together, nitrogen still has a lone pair here represented by the 2 electrons that came from its 2s subshell, but each of these orbitals here is only an unpaired electron, which means that each of these can combine with other elements in order to form sigma bonds. So again, this orbital here corresponds to its lone pair here, whereas each of these orbitals here originally was an sp3 hybrid orbital with only an unpaired electron. And then when hydrogen brings its unpaired electron in, it combines with these unpaired electrons here in order to get 3 pairs, which results in 3 sigma bonds once again. And this same idea can occur with oxygen as well. Again, bonding does not happen unless the orbitals in its valence shell hybridize or combine together. So if we write the hybrid orbitals for oxygen, same as nitrogen, the 1s subshell is unaffected, and the 2s and 2p subshells hybridize together to give us 4 orbitals that are at an equal energy level, the 2s P3 subshell. But here, because oxygen already has 2 pairs filled in, these would also be filled in like this, and the 2 unpaired electrons would exist in these orbitals here. And again, we know that this is correct because oxygen has 2 lone pairs starting, and these orbitals here would correspond to the unpaired electrons in these 2 sp3 orbitals here. And once again, that means that they can pair together with hydrogen's unpaired electrons in order to produce sigma bonds once again. Finally, there is a third type of bond that can form when lone pairs are able to interconvert between bonds. So as we'll look at when we start looking at acids and bases, we can actually get a bond that forms where both electrons come from the same element. So for example, if this water molecule here uses 2 electrons to form a bond with this hydrogen here, we know that hydrogen can only make 1 bond, which means that this bond is going to break and its electrons are going to move over here. And because these 2 electrons formed a bond with hydrogen, we would now end up with a strange molecule called H3O+. This will become very important when we start talking about acids and bases, but if we assume that this lone pair was used to make this bond here, again, we're forming a bond using 2 electrons, but instead of those 2 electrons coming from separate atoms, they're only coming from a single atom because these 2 electrons used to be a lone pair. So this is still a sigma bond, but this sigma bond is a little bit different because of the origin of the 2 electrons, and for that reason, this is what we call, or this bond here is what we call a coordinate bond. Again, distinguishing it from a sigma bond because the 2 electrons came from 1 element rather than from unpaired electrons from 2 elements. In the next video, we're going to look at how we can get different types of bonding other than sigma bonds. This will explain, using the quantum model, how double bonds and triple bonds form.